Good morning, students. Good evening or good afternoon. Thank you for tuning in to Chemistry with Ms. Hernandez. We're going to be covering today periodic trends, ionization energy, section 6.17. But today, instead of using CK12 like we've been doing this whole time, I have made a presentation out of this. So we're going to use something different, okay? Something just a little bit different. It's the same information, it's just in a presentation mode, okay? So we're just changing it up just a little bit. Here you have your topic. Keep this image in mind. You have your nucleus, protons and neutrons. You have your electrons that are floating around in the cloud. And all ionization is the energy needed to release electrons or remove an electron. Okay, so let's get started. I need to get that. Okay. So this is our introduction. As you can see, it's exactly the same as what you have here. Why do sheep travel in herds? All right, who's going to read for me? I need a volunteer. Yeah, Alexia? Okay, anybody else? Gabby or Oscar? Anybody else? I need somebody to help me read, please.
I'll read it.
Thank you.
Like many other animals, sheep travel in herds. The tendency is for each individual sheep to stay with the herd. However, a sheep may sometimes wander off, depending on how strong the attraction is for a particular food or water supply. At other times, a sheep may become frightened and run off. Whether a sheep chooses to stay with the herd or go its own way depends on the balance between attraction to the herd and attraction to the outside influence.
Thank you.
The other paragraph?
Oh, no, I got it. Okay, so most animals travel in herds, right? Or in a pack. And most of the time it's for safety reasons, right? It's a lot safer to stay in a group because if somebody attacks, you can fight them off as a group, right? But sometimes animals get distracted, whether it's water that they want, that they see close by, that they think they can get to, or food, okay? But there's always an attraction for sheep and for animals to stay with their pack or their herd because we know that that's where they're safe. Okay, so is that water creating a greater attraction to the water than to the herd? Is that food that's available gonna beat the attraction and the safety of the herd? We don't know. There is a delicate balance. It all depends on that one animal and what the need is for that particular animal. The same thing happens with atoms. There are parts of the atom that have a certain relationship. And here it talks about electrons and protons. There is an ongoing tension, a relationship between electrons and protons in an atom. Now, an atom's reactivity, how it reacts with other atoms, depends on, in part, on how easily electrons can be removed from that atom. We can measure this quantity and use it to make predictions of behaviors of atoms. All right, so we know electrons and protons, they should have a certain chemistry, a certain attraction to each other that pulls them together, right? Positive and negatives have a tendency to come together. Well, for certain electrons that are far away from the nucleus, it might be easier for it to remove than to stay with the nucleus, okay? And that movement creates a reactivity with other elements. Okay, so let's get started with the topic. So ionization energy. What is ionization energy? Ionization energy is the energy needed or required to take away or remove an electron from a specific atom. The measurement, it's measured in kilojoules per mole, which is a unit of energy, just like calories, right? Ionization energies associated with some elements are described in the table that you see here. Okay, and this table tells you, okay, well, ionization energy 1, ionization energy 2, 3, 4, 5, and 6. Atoms can lose up to 6 electrons for this table. Okay, but look at the ionization energy for electron number 6. If you have already removed 5 electrons and you're going for that 6 electron, it's going to take a lot of energy to take away that electron. Look at that. For carbon, if you're working on electron number 6, it's going to take 47,000 kilojoules per mole in order to get rid of that electron. Versus if you're talking about the first electron, right? If you're talking about electron number 1 that's trying to get, take it away, well, that energy is 1/40th of what was required for electron number 6. It only takes 1,086 kilojoules per mole to get rid of that 1 electron. Okay, and as you can see, look at this. Ionization energy is really, really high for hydrogen and helium, and then it gets lower and lower and lower, and then it gets high, high, high. Okay, we're going to talk about that trend that you see here. For any given atom, the outermost valence electrons will have lower ionization energies than inner shell electrons. Okay, so let's go back to the picture that we were talking about. These electrons on the outside are valence electrons. These electrons on the inside are known as inner electrons. So ionization energy will be very low for electrons on the outside than it is for electrons on the inside. That's all it said. As more electrons get added to the nucleus, and I think that might be a typo because electrons don't get added to nucleuses. They get added to the cloud. What gets added to the nucleus is protons. So there might be a typo there. As more protons get added to the nucleus, the outer electrons become shielded from the nucleus by inner shell electrons. It kind of does like a little blocking thing, right? Just like in football, when those linemen are blocking those people from getting to the quarterback, these inner electrons shield that nucleus from those outer electrons, okay? Keep this in mind. And what is that called? It's called shielding. Okay, you are shielding those outer electrons from the pull of that nucleus. Okay, you're protecting the quarterback, right? Those inner electrons are protecting the nucleus from those outer electrons so that those electrons can get removed. Now, you have a statement that you're going to be answering. And this is for the people that are live. Guys, my students, right now, 5th period. Is this statement true or false? Ionization energy is the amount of energy needed to gain or accept electrons. True or false? All right, let's wait for responses from my students. If you are live, what do you think? Is ionization energy about gaining electrons? True or false? I got one person that says it's false. 2 people that says it's false. What about the rest of my students? Is anybody else in here? Oh, 4 votes for false. If you're not in here, I'm putting the code in the chat so you can get in here. 5 students have chosen false. Very good, guys. You're listening. That's good. You're paying attention. Why? Because I know that statement is completely false. Okay? Ionization energy is not about gaining and accepting electrons. If we go back to the reading, Ionization energy is about removing electrons. Very good, guys. Second period didn't do as good as you guys. Good job. All right. All right. So that was a false statement. All right, so here we have first ionization energies for versus atomic numbers for main group elements. Now let's look at this. So here you have your elements, and they're by atomic number. Okay, they're not by the name of the element. It's all about the atomic number. Over here you have the energy needed to remove electrons, and EV means electrical voltage. Electrical voltage. At least I think that's what it's. I'm pretty sure it's. Okay, so if you have electrical voltage and you're looking at element number 1, hydrogen, it's going to take about 13 and a half electrical volts to take away 1 electron from hydrogen. And look at how much it jumps for helium. It's almost double the amount. Helium takes up almost 25 electrical volts in order to take away 1 of those electrons. And then it goes down, and then it goes up. And then it goes down, and then it goes up. This is a trend, okay? We can see the further down we go, the bigger your atomic number, the lower the ionization energy becomes. Look at that. It started off high. Look at hydrogen. It was at about 14. Everything, almost all the other elements are below 14. So we can say as we go further and further down the periodic table, ionization energy should get lower and lower and lower. That's one thing that we have observed. Okay. Now, let's talk about the trend, right? There's always a trend down a period, and there's always a trend down a group. Let's talk about that period trend, going left to right across the periodic table. Anytime you're moving from left to right across the periodic table, ionization energy for an atom is going to be increasing. It's going to get higher and higher and higher. We can explain this by considering the nuclear charge of the atom. The more protons in the nucleus, the stronger it gets, right? That nucleus is getting stronger and stronger and stronger, so it's going to be pulling those electrons closer and closer and closer, and it's going to say, nah, you're not going anywhere. It's going to take a lot of energy for you to go away because I'm really, really strong. I don't want to let go of those electrons. The stronger the attraction makes it more difficult to remove electrons, so you're going to need a lot more energy. So energy will increase as you go from right to left, meaning it's getting higher and higher and higher. On the left side, it's low. On the right side, it's going to be high, okay? Where helium is, it's high. Where hydrogen is, it's low. All right. What about groups, miss? If we're going up and down a group, what's going to be the trend? Within a group, the ionization energy will decrease as the size of the atom gets larger and larger, okay? As you go down a group, it's going to get low, 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 low. Energy is going to be low. So it's high on top, low on bottom, okay? We see the ionization energy increases as we go up a group to the small atoms, to the smaller atoms. In this situation, the first electron is farther away from the nucleus as the atomic number or the number of protons increases. Being far away from the positive attraction makes it easier for that electron to be pulled off. So imagine, and the way I always like to explain this is if you have a big family versus a little family. If you have, or if you know somebody who comes from a big family with lots of brothers and sisters, right? All of these electrons that you see here are brothers and sisters. Your nucleus, that's mom and dad. So the older you get, right? I have all these other brothers and sisters that are here. So once this guy on the outside turns 18, Well, what's mom going to tell him? Is mom going to say, ay, no, mijito, ay, quédate en la casa? Or is mom going to say, hey, you need to go to work. You need to go to work because we need help at the house to feed all your other brothers and sisters. Okay? So as your atom gets bigger and bigger and bigger with more and more electrons, this electron is easily going to go away to bond with somebody else because energy, that pull from the nucleus is going to be a lot less, right? Because he's so far away. Now, if I compare that to a small atom, right, or a small family with just 2 electrons, that nucleus, mom and dad are not going to want to let it go. It's going to take a lot of energy for this electron to go away than it would if it was in a bigger atom. Does that make sense, guys? Does that make sense? I hope it does. Okay, the bigger the atom, the further and further away those electrons get, the easier it is to go away. Ionization energy will be very, very low. Okay, now let's check your understanding. Let's check if you're able to understand by answering these questions. And don't worry about the multiple choice in this one. I wasn't able to change the answers. Okay, so the answers have nothing to do with this question. All right, so here, which element has a lower ionization energy? Which one's lower? Is it beryllium over here on element number 4? Or is it nitrogen, element number 7? And you can just answer it in the chat, guys. You can answer it in the chat and I will tell you yes or no. Who is lower? So they're in the same period. So we know that the trend is that it increases. My question is, who has lower ionization energy? Beryllium, number 4, or nitrogen, number 7? What do you think, guys? What do you think? I'm looking at the chat. That's where I'm looking at. Which element is lower in ionization? Beryllium, the one that's closer to hydrogen, or nitrogen, the one that's closer to helium? Okay. Where is ionization energy considered to be low? Very good, Oscar. He says he thinks, Miss, it's BE. And you know what, Oscar? You're correct. You would get 100 for that answer. Why? Because it's more to the left. The more left you are, the closer you are to hydrogen, the less ionization energy you have, lower ionization energy. The closer you get to helium on the right, the higher the ionization energy. Very good, Mario. Very good, America. Very good, Oscar. I see your answers. Now, question number 2. Let's see if you can understand this one. Which element has higher ionization energy? Aluminum or indium? So if you can see here, aluminum is on top, indium is on bottom. Our trend says that ionization energy decreases. So what will be our answer? Oscar and America have already posted in the chat. They think it's aluminum, and guess what? They are correct. If you are at the top of the periodic table, you have small atoms. Small atoms have high ionization energy. If you have a big atom with lots of electrons, lots of brothers and sisters, the amount of energy to remove electrons will be very low. Very good, guys. Oops, my bad. Very, very good. Oh my God. You guys are awesome. My 4th period class had a real tough time understanding that. Very good, guys. You guys are real sharp today. All right, so we got a video that we're going to watch and we're going to summarize after that.
Ionization energy. Ionization energy is the amount of energy required to remove the highest energy electron from an isolated neutral atom in its gaseous state. So, atoms want to keep their electrons. Some atoms want to keep them more than others because depending on how close and how tightly bonded the electron is to the nucleus, the more difficult it's going to be to remove that electron, and so that means that's going to be a higher ionization energy, will require more energy. Now, the first ionization energy is the energy required to remove one valence electron. The second ionization energy is to remove the second valence electron, and so on and so on. So they're named after how many electrons you're taking. But they always increase in energy. It always takes more energy to get that second valence electron than it takes to get just the first. So second ionization energy is always greater than the first. And it's important to remember, like we said, that when the electron is bonded very closely, so when the atomic radius is very small, this has a high ionization energy. And when it has a big radius, so if we have a bigger radius, this has a lower ionization energy. Because it's further from the nucleus, because this radius is bigger than this small radius, it is going to take less energy to take that first valence electron. And depending on how many valence electrons that element or atom has to give or wants to give away, that is going to determine how much the energy increases from first ionization energy to second ionization energy. Now, there is a periodic trend for ionization energy. Ionization energy increases from left to right across a period, and ionization energy decreases from top to bottom in a group or family. Now, when we have a periodic table, when we move from left to right, remember that ionization energy increases. So ionization energy increases. And remember, this is because the atomic radius decreases due to the increasing electronegativity, so the attractive force of the nucleus on those electrons. So it makes sense that as I go from left to right, the electronegativity increases. So that means the atomic radius is getting smaller. So atomic radius gets smaller. And that makes the ionization energy increase because you're going to take more energy to get that electron that's closer to the nucleus to get away from that nucleus. Now, when we go down the group in the periodic table, ionization energy does the opposite. It decreases. It decreases because we know that electronegativity goes down as we go down the periodic table. When that happens, that means the atomic radius also increases, making it further and further away, meaning there's less energy to take that electron. So taking the electrons from this CS is going to be easier than taking it from RB because the atomic radius is bigger, the electronegativity is less, so it's going to take less energy to take that electron.
Okay, so he just gave us another version of what we already talked about. All right, so we're done with that one. Let's see what's next. Okay, so in summary, ionization energy refers to the amount of energy needed to remove electrons. The second point to today's topic is ionization energy decreases as we go down a group, right? As we go down, we know that those atoms are getting bigger and bigger and bigger. Those electrons are going further and further away. They're going to be easier to get rid of. So as you go down, ionization energy gets lower and lower and lower. Now, what about ionization as you go from left to right? As you go from left to right, it's going to increase, meaning it's going to get higher and higher and higher because that nucleus is getting stronger and stronger and stronger. So it's going to pull those electrons closer, and it's going to be a lot harder to get rid of or to take away electrons, okay? Now, these are your review questions. You are going to do only the first 5, okay? We will skip number 6. I don't like it. It didn't really get talked about in today's topic, in today's reading, so we're going to skip it, okay? All right, so let me stop this real quick.